Okay, I'm going to recap the insert algorithm for the B plus tree index, and then we will cover the second version of the insert algorithm. You're given a search key, and then you're given an index that is indexed on the search key, or the index key that is indexing a file. And now you are given a query that contains the value for that search key. You need to retrieve the correct records that match that search key. The first thing is to just search for that. So you use the search algorithm. And then if there is space in that leaf, you go and insert the new data entry into that leaf. Oops, sorry. If it doesn't have space, that's when the tricky part arises. You need to split the leaf into two new leaves. Let's call them L and L prime. And then you have to redistribute the data entries on that leaf across these two new leaves. When doing so, you need another index key present in the parent of this leaf, or the parent of these two new leaves, to tell these two leaves apart. And for that, you copy up the middle key based on the keys that you redistributed. Then you insert the index entry in the parent pointing to L prime and L. If that parent itself is full, this new index entry addition might cause the parent to split. Then you basically do the similar procedure. You add a sibling for the parent, redistribute the index key and the page pointer entries across these two nodes, and then you push up the middle key rather than copy up, because in a B plus tree index, there should not be any redundancy in the index key values in the index pages. Okay? Every index key entry in all the non-leaf pages should be unique. And if it keeps happening all the way to the root, then the root itself splits, and then you get a new root, and therefore the height of the tree grows by 1. Okay? And this is the illustration we had. This is the state of the tree as it is given to you. I won't tell you how it came about. This is just the tree that is given to you. It's the state of the tree now. And now you're asked to insert a new data entry with search key 8. And so you first use the search algorithm, and then figure... I think it fell behind. Oh, it's under you. So you find the search algorithm. You basically locate the leaf where this data entry should go. There's no space here. Split it. Redistribute the entries. Notice that the sorted order of the index keys is still maintained. Copy up the middle key. In this case, the middle key is 5. Add that to the parent, but now the parent is full, therefore the parent splits. Since the parent is the root, the height grows. And so now you have this new entry in the parent, 5. The middle entry of the parent, which is 17, is pushed up, and that will be the new parent. Notice that the minimum occupancy of 50% is still satisfied for these non-leaf pages. The only node where that occupancy can be violated is the new root. And so this is the state of the new index after the insertion is done. Okay, so the recursive splitting all the way up to the root, and therefore the height grows. Now, the alternative algorithm for the insert is, can we avoid these sorts of splitting in some cases? Because the splitting is expensive, you'll have to add a new page, you have to change the page pointers and stuff. It could become expensive because the new page that you add could be elsewhere on disk. Notice that all of these pages must have counterparts both in memory and disk. So now you're adding a new page to this index file, it will be added in some other location on disk. So then you will end up doing a lot of random access when you're using the index later on. And you also notice that there's a lot of free space in a bunch of these other leaves. So the next natural question is, can we avoid splitting by claiming some of the free space from the siblings? Okay, so this is the other idea of redistribution with sharing data entries with siblings, and this is only possible if your sibling leaves have free space. So here's an example for redistribution across leaf nodes. Same example, so you're inserting 8. You come down here, and then notice what I did there. You notice that the right sibling, so you know the 8 will bring you here because this is what the search algorithm tells you. There is no space to the right of 7 on this leaf. So now, normally you would just split this leaf. But now you notice that based on this pointer that you have at the leaf level, the neighboring leaf has 2 extra spaces. So maybe you can use one of those. And so what you do is you throw the 8 into the neighboring leaf's lowermost space. Okay? But then there is an issue. What is the issue?
The parent. 13.
Yes, the parent becomes inconsistent. The rule says that you should only take the right pointer if your values are greater than or equal to 13. 8 is actually less than 13, so it's violating the B plus tree's conditions. So all you need to do after you do this is to update the corresponding index entry in the parent. So no, you're not inserting a new index entry, you're just updating the index entry in the parent. Okay, so here, by redistributing the data entries and sharing the free space across the siblings, you're avoiding a lot of extra splits. This is usually not used for non-leaf node splits. It's used for leaf node splits because non-leaf node splits, the number of non-leaf pages is small anyway relative to the number of leaf pages. You can still fit them in memory even if you split them. Whereas for leaf pages, they are usually disk resident. And so splitting leaf pages is actually more expensive in most cases. And it also increases I/O costs because leaf pages usually are not entirely going to fit in memory. Taking this pointer and then going and getting this page would involve a random disk I/O. Okay? And random disk I/Os are expensive. They could take milliseconds. Whereas random memory access is microseconds. Okay? Internal splits, if you do have internal splits, it is actually good because the capacity of the tree to index more pages grows exponentially in the level at which the tree is, the node is being split. We discussed the number of leaf pages that can be indexed by a tree of height 1, height 2, height 3, and so on. The number of leaves that can be indexed is exponential in the height of the tree. So if you have a split in one of the non-leaf index pages, the capacity of the tree could grow. And that is actually good because it will amortize your cost. You pay that cost once. Now for a large number of insertions, you don't have to split anything in the future. Whereas at the leaf level, if you do a split or not split, it doesn't affect the capacity of the tree significantly. It only reduces the space by 1. So the other one is pointer management headache. So now if you do this in the internal leaf pages, you'll have to update the pointers of the parents and make sure that the entries are updated. Now that's just extra bookkeeping overhead. If you do the splits, you're basically amortizing all those sorts of overheads over multiple insertion operations. So the rule of thumb for practical purposes is to use this sort of redistribution across siblings only at the leaf level. And if a split is necessary, when would this procedure fail? This sibling has no more free space, then you can either go and check the other sibling, and then it becomes hopelessly complicated because now you have to keep track of 2 index keys in the parent and so on. So typically this algorithm is not done for anything more than just the left or the right sibling. You don't keep chasing the pointers to all the way to leaf with free space. Whereas for the internal index pages that are all the non-leaf pages, if it fills up, you just try to split it up. Okay? Any questions about insertion? Yes?
Is there possible the case that when we do splitting, we have this range of keys that is smaller than the number of keys we can hold inside one page? That is, we can waste some space inside a page for the keys.
Could you repeat the question? Like, what do you mean? Like, you don't have enough entries?
Yeah, I mean, like for 13 and 17, we have this 4 slots available in between, but we only have we have 5 slots in between available. Like we will waste 1 slot between 13 and 17. You know.
Oh, these slots are occupied in increasing order based the way you depict is left to right.
Yep.
If there is one free slot over here, that usually will not happen unless you have deletes. So if you have free slots over here, that means you have some deletes. Then that is okay because the occupancy is still 50%.
Okay, but so, I mean like for the leaf node, we for the second pointer from 13, it points to this leaf node.
Yes.
What if this leaf node actually contains like 5 slots? We decide to have 5 slots, but for 13 and 17, we only have 4 numbers available inside this range. So we will waste 1 slot in this case, right?
No, you could have more entries here than the index pages. That is okay. There's no need that the number of index key values here should be the same as the number of index key values in the non-leaf pages.
Okay.
Because you could have, say, between, so in this particular example, because you have 13 and 17, you could only have, I don't know, 14, 15, and 16 over here. Actually, 13, 14, 15, 16.
Yeah.
Okay? But in general, this could be something else. This could be like 21. Then you could have more entries that are acceptable here. Does that make sense? In this particular example, it so happens that you have these two numbers. But when you actually build the index from scratch, you will make sure that sort of situation doesn't arise. Okay?
I have one more question.
Yes.
And previous slide.
Yeah.
Yeah. If the second node we still have 4 elements, which means it is full, do we have to like propagate it to the next until we find an empty space? Is that correct?
Right. Yep. So when you have empty space, you basically have to do an insertion sort kind of thing. So you just have to figure out which location it goes in, and then move these things across the slots.
Okay.
Notice that all of this is within a page, so it's all in-memory operations. And so it's just a mem copy. So it's very cheap compared to this guy. Okay? Every entry in the leaf page and in the non-leaf page, you depict them in sorted order. Okay? Great. What happens when you have to do a deletion of a record? So just like with the binary search trees, deletion means you have to reorganize the tree. Here also you might have to reorganize the tree. Again, the delete algorithm starts at the root, find the leaf where the entry with the given search key belongs, and then remove the entry. That's it. If you have a record which has the same search key as what you're given for your delete query, remove the record from the leaf page. The problem arises when the leaf now goes below 50% occupancy. Okay, so if the leaf is no longer at least half full, then you have a problem. If the leaf is still half full after removal of this entry, you have no problem. So what happens if the leaf underflows? If its occupancy goes below 50%, then you have to do something. And here, the first thing you want to try is to redistribute the keys from the siblings. Notice this is the inverse of what we did for insertion. Insertion, at the leaf level, we try basically to, we try not to do the sort of redistribution across leaves because you want to make sure that you don't do extra IOs. Whereas for deletion, the first thing you want to try is redistribution across siblings. You look at your left sibling and your right sibling, and then try to figure out if you can borrow keys from them, like move keys from them, and then that'll ensure that you have at least half full. If that is not possible, if your siblings are also close to just half full, then if you move a key from a sibling, then the sibling might underflow. So then you have a problem, and in that case you will have to merge yourself with your sibling and form a new leaf. Okay? So I will illustrate this later, but this is the algorithm. Now if a merge occurs, that means the index key in the parent that split the sibling and you will have to be removed. And this might have to propagate upwards recursively if the parent starts to underflow. Okay, and all the way to the root. If the root underflows, if it's basically you're saying one index entry has to be removed, that is fine. Notice that the root is allowed to have less than 50% occupancy. If one of the index keys is removed, then that means if all the children in that level are gone, so then your height for the tree decreases by 1.
Yeah, I have a question.
Yes.
And here we have to check whether we can redistribute first.
Exactly.
When it comes to insert, do we have to like check it first as well?
So when it comes to insert, at the leaf level, you try not to redistribute.
At the leaf level,
Yeah. You try not to redistribute at the leaf level. So it's usually, sorry, I guess I spoke it wrong. So for the non-leaf node splits, you don't do the redistribution. So that means at the index page level, you try to do the redistribution in only for the deletion. For the insert, if you have to split the index page, you do that because the capacity of the tree can grow. So for the leaf level, you can still try to basically figure out redistribution is fine. Okay. So the same thing happens here, except here the redistribution is the first preference for both the leaf level and the non-leaf level. Okay? Yeah, sorry for the confusion. Okay, so again, if the underflow happens in the non-root, non-leaf page, then you have to keep propagating the merge all the way up to the root, in which case the height might decrease. So here's an example. This is the state of the tree as is given. And this tree has one non-leaf, non-root level. It has the root, and it has a leaf. What is the height of this tree? 2. Yes, the height of the tree is 2. If you have only the root in the tree, that's height 0. This is height 1, this is height 2. Okay, so you count from 0. Okay, so now here you see that there's a occupancy of less than 50% at the root. The occupancy is 50% here and here, so that means the order of the tree is 2. So you can fill up to 4 keys here. Every leaf page has at least 2 entries. Okay? So this is a valid B plus tree. Now you're asked to delete the record with search key 22. What do? Do the search algorithm, you find this is the leaf page, delete that entry. Okay? How did you get here? 22 is greater than 17, you come here. 22 is less than 24, you come here. Then you delete that record. Fine, nothing wrong. The leaf page is still 2 entries. So this tree is also valid. Now you're asked to delete a record with search key 20. Again, you chase the correct entries, you come here, and then you delete that record. But now you're stuck because you have to do something with this leaf page. You cannot have less than 50% occupancy. Okay, so what do? You try to redistribute the keys from your siblings. Look at your left sibling. It's already at 50% occupancy, so you cannot borrow from your left sibling. Look at the right sibling. You have more than 50%, and if you borrow 1 key, this sibling will still be at 50%. And therefore, you borrow the key from the right sibling. Okay? So what happened here was the lowermost key value from the right sibling moved here, which means the index key of the parent that splits these 2 siblings has to be updated. So let's do this again. 22 is gone, no issues. Delete 20, 20 is gone, but now you have an issue. We are underflowing here. You're going to borrow 24 from your sibling, but if you put 24 on the left leaf over here, this is no longer valid because our convention was if you're strictly less than 24, you go to the left. But because 24 will now come to this leaf, this index key has to be updated, and the way you do that is by copying the middle key up. And the middle key here is 27, and so the index key is updated to 27. Okay, so now the consistency of the tree is still there because anything to this side is strictly less than 27, anything to this side is greater than or equal to 27. Okay, does that make sense? So the middle key is 27 and it's copied up to the parent. Yes?
Is it true that you can always find a sibling because in the non-leaf you have to have at least half the
Yes. Now if both of your siblings are exactly at 2, right, then you're out of luck. And that's what's going to happen next. Okay, now I'm asking you to delete the data entry with search key 24. So the current state of the tree is this, follow this, you come here, and 24 is basically going to be gone. At this stage, you would have to merge the leaves. So here, if you see, watch carefully, so here this is 24. Once you delete 24, you have only 1 entry in this leaf. And that's not good, because the occupancy is less than 50%. Whereas here you have 27, 29, here you have 33 to 39, and then there's 30 over here. What you do is you merge these 2 leaves. Okay? And then you get, after deleting 24, 19, 27, and 29 form a single leaf, 33 to 39 is the other leaf. The parent, if you see the parent, there was 27 in the parent over here. Because these 2 leaves are merged, this entry in the parent is going away. And that means the parent is left with only 30. All of these entries here are less than 30. All of these entries here are greater than or equal to 30. And so now this is the temporary state of the tree. But this is not a root node. You cannot have less than 50% occupancy for a non-leaf, non-root index page. And so you have to basically, after merging these leaf nodes, you remove this entry in the parent, and now you need to recursively merge upwards. To do so, you have to do something called the pull down of the index entry from the parent. So here, if you see the state of the parent is 17 over here, 5 and 13 over here, and then after these 2 merge, this entry goes away and then you have only 30. Okay, so then what you do for pull down is you take the entry from the root, and then you pull it down, and then you fuse all 3 of these into a single node. And so the way this ends up being is you get a tree of this sort, because the root itself had only one entry, you're not able to pull down multiple entries, and therefore all the 4 keys are merged into a single non-leaf page that becomes the new root. And because the root has been pulled down to its next level, the height of the tree has gone down by 1. Notice that this is the new page, the leaf level that you created by merging the 2 siblings. The other pages are still the same. The pointers, left of 5 is still the same, right of 5 is still the same. All of these pointers are the same. The pointer to the left of 30 is now inserted here. The pointer to the right of 17 is consistent. So this is the new consistent valid P plus tree after the delete and the recursive merging. Any questions? Yes?
Does it have to merge with the right sibling? Does it can merge with the left sibling?
You can merge with the left sibling as long as you're on the right. So here, when you had an underflow, right? When you had an underflow over here, the left sibling is actually, the left leaf is actually not your sibling. The left leaf is actually your first stuff, because your cousin first removed or whatever. Your right leaf is your sibling because you share the same parent. Okay, so if you're this node and this node underflows, then you have 2 siblings. Okay, so then you can actually merge with either of them. But this node unfortunately has only 1 sibling. Okay.
If it's 2, then you can choose either one.
You can choose either one. Yeah. If both of them, if you're unlucky enough that both of them are now underflowing, then you can choose either one. Okay, so that's your final state of the tree. The pull down of the index entry means you take an index key from the parent and then merge it with your sibling, and then now you have a set of index keys. If that parent happens to be the root and it has only 1 index key, the root is merged with its children, and therefore the height goes down by 1. Okay, so this is your delete operation, and in project 2 you will be asked to implement the insert and the delete operations. Okay, so go and read the textbook, the call book, to make sure you understand this correctly, and then you'll have to be implementing this in project 2. Okay, so now, as I mentioned, you can do this sort of redistribution of keys across non-leaf nodes as well. So here's, say, a state of the tree, and this is not related to the previous example. This is a new state of a tree that I'm giving you. So in this case, you see that this occupancy is less than 50%. Instead of trying to pull the root index key down and then merging it with a sibling, here in this case that is not possible. What you would do is look at your sibling. So in this case, this node is underflowing. It looks at its sibling, but the only way you can do that, you don't have doubly linked lists over here. So you have to make sure that you know the parent and then the parent's pointer and the child. All of these need to be available. And then you see that the sibling is full, so you can redistribute some of these keys to this node. And the way that would work is just like we saw with insertion. You would take some of these entries and then put them over here. 5, 13, 17, so let me do this again. 5, 13, 17, 20, 22, 30. Okay, so now you have to make sure that the order is preserved, and so 20, 22, you'll have to move it to the right sibling, and that is called a rotate operation, because you basically take the keys, go up like this, and then come down here. Okay, does this make sense? So 20 and 22 have moved to the right sibling, and now the occupancy is at least 50% in both cases. Because 20 and 22 moved here, the parent's index key has to be updated. The parent's index key is now 17, which was the middle key. Okay, does that make sense? And you had some page pointers over here, here, and here. They were pointing to these 2 pages. So if you look at the state of the tree before, this pointer pointed to 17, 18, this pointer pointed to 20, 21. But after you do the rotation and you move 20 and 22 here and 17 here, these 2 pointers will become empty. And all you need to do is take this pointer and put it over here, take this pointer and put it over here. And so after rotation, you end up with this sort of pointer layout. Less than 20 comes to this page, less than 22 comes here. Okay? The others are still the same. Here the others are still the same. Does that make sense? So the rotate basically means you're redistributing across non-leaf siblings. You have to make sure that the index key of the parent is updated by moving the middle key up. And you have to make sure that the page pointers are correctly swapped to the new sibling where the new index keys are. Okay, so this is, again, not rocket science, but you have to make sure it's carefully done so that the tree after your update is still consistent. It does not violate the requirements, which is anything left should be strictly less than, anything to the right should be greater than or equal to. Does that make sense? Any questions? So these are all just efficiency tricks for avoiding a merge of the nodes and avoiding the height of the tree to be reduced. The reason these tricks help is you keep the capacity of the tree to be just above 50%, so that now if a new insert operation comes in the future, you can actually add them to the leaves, and you have entries that can absorb those additions. Notice that B+ trees in the real world, you can have a bunch of inserts and then deletes and then inserts and then deletes. All sorts of mix and match can happen, and so you really want to make sure that you're not optimizing for just inserts alone or optimizing for deletes alone. You need to have a balance of the two. Any questions? Okay. Now, in insert, redistribution is discouraged for the non-leaf nodes. And why is that? We just discussed during insertion in the non-leaf nodes, which is the index pages, you try not to do redistribution. If it's overflowing, then you want to do a split. Why is that?
Splitting doesn't like restructure the whole tree. Doesn't comparing to the.
It might.
We don't get the height benefit from having, he mentioned something about sending the height of the tree gives us more space.
Yes, exactly. If you do redistribution, the tree will still be fully occupied or close to fully occupied, which means future inserts will cause performance issues. If you do the splitting, the capacity of the tree grows. So now it can absorb more inserts without having to grow. Okay, so that's why redistribution is discouraged for non-leaf nodes during insertions, but during deletions you actually prefer redistribution over merge. And this is true for both the leaf level and the non-leaf level. Okay? And this is for a simple real-world reason. There is no algorithmic reason. Files usually just grow. Deletions are very rare in the real world. Okay? When you have a data set of customers, it's very rare you actually go and delete a customer record. You just keep adding customers. The company keeps growing. Unless your company shuts down, in which case your database is switched off. Okay, so deletions are pretty rare. Files usually grow, relations usually grow, and therefore inserts are more common than deletes. And therefore, if you do a delete, you don't want to shrink the capacity of the tree. You don't want to do merges too often. You rather want everything to be close to its 50% capacity so that it can absorb future inserts. And that's why deletions, you prefer redistributions over potential mergers at both the leaf and the non-leaf level. Okay? And redistribution is usually likely to be very successful when you have a fully grown tree based on a file that you're indexing. And we'll talk about how do you create a fully grown tree. Redistribution is quite possible that you will succeed because of the fan-outs of the tree. The number of entries in each of these leaf and non-leaf nodes will be such that you will almost always be able to find a sibling that has a key that you can move to yourself. Okay? And when you do redistribution, you only need to propagate changes to your parent. Whereas if you do a merge, you might end up doing recursively all the way to your parent's parent and all the way to the root. Whereas if you do just the redistribution, all you need to do is pointer swaps. We talked about the pointer swaps, how the page pointers are now moved to another location. And the index keys are updated. So these are all very tiny in-memory operations. Any questions? Okay, so the next thing about B+ trees that you need to be aware of is, even though the index pages have unique index keys, you could have records that have the same search key or the same index key. Like when you're indexing the movies table on year, you could have multiple movies having the same year. So in which case, what do you do? If you follow the alt-RID list, there is not going to be any repetitions of the index keys at the leaf level. But if you follow alt-RID, you are going to have repetitions if that attribute is not a candidate key. It is likely that there will be repetition. Now, another possibility is that, Another possibility is that a single data entry could span multiple pages. This could happen if you are indexing on strings, okay, like addresses or even reviews. So what do you do in these cases? When you have these sorts of repetitions, all data entries with a given index key value, you want to try to make them reside on a single page. And then you use what are called overflow pages that are not part of the leaf list. Okay, so these sorts of duplications of data entries with the same index key or single records in the alt record alternative being very large, you basically have what are called overflow pages that are orthogonal to the leaf list of pages. The other alternative is you allow repeated index key among the data entries, but for that you need to modify your search algorithm appropriately. Okay, so if you have repetitions in your data entries that have the same search key, then your search algorithm has to be aware of what exactly you're looking for. If multiple leaf pages have the same index key value, it's very hard to figure out how you're going to detect which route to take from the root. In that case, you could either combine the record ID along with the index key to get a unique composite key. Okay, so that's just one way of avoiding these overflow pages. So the overflow pages are basically pages that point from the leaf, that are pointed to from the leaf, but they're not part of the leaf list. Okay, so then you just take a route to a leaf, and then if the records all have the same index key, they will be pointed to from the leaf to an overflow page, and then from the overflow page to another overflow page. Okay, does that make sense? So this is how you would handle repetitions of the data entries, search key or index key values in the B+ tree. Okay, now I talked about the occupancy and the order concept. So the order concept basically counts the number of entries in your non-leaf pages, and you want to make sure that it's at least half full in terms of the order. That means your occupancy is between D and 2D entries. But because you could have variable length fields, in practice you replace this order concept that is counting the number of keys based on occupancy in terms of number of bytes. So the page needs to be at least half full with valid bytes. Okay, so this is useful because of two reasons. In the non-leaf pages, you could typically have many more entries than leaf pages, especially if you're following something like this, alt record, or if you're following alt RID list. If you're doing alt record, the data record could be very large, which means in a leaf page, you can only pack so many data entries. Maybe say, I don't know, a couple of dozen. But on the non-leaf page, you could pack maybe, I don't know, 10 dozen entries. And in this case, instead of having the same notion of order for the leaf and the non-leaf, you replace it by just counting the raw number of bytes on the page that are occupied. Same thing for alt RID list. We talked about how alt RID list, the entries are variable length because you could have multiple records for the same index key value, but the number of records per index key value could differ across index keys, which means the entries in the leaf page are of variable length. Different nodes could also have different number of entries because of variable size index key. So we talked about how you can index on a fixed length domain like integer or floating point or characters, but then you could also index on variable length characters, varchar, or strings like text columns, in which case your index key could be arbitrarily long. It could be 100 bytes or it could be 2 bytes. So because these index keys are of variable length, there is no uniform way to compare the order concept across non-leaf pages, and therefore you only go with the physical criterion, which is half the bytes are valid on the page, the rest are free. Okay, does that make sense? And the same holds for alt record with variable size data records because you have variable length entries, and for alt RID list. Does this make sense? So this is why we replace this logical notion of order, which counts the number of entries, with a physical criterion that just looks at are at least half the bytes not free. Okay, so how does a B+ tree come into existence in the first place? I showed you states of trees and then asked you to do inserts and deletes and stuff. The most common way is you have a relation that is stored as a heap file or whatever, and then your database administrator comes in and then writes an SQL query that says create index on. Okay, so the create index on statement in SQL does what is called bulk loading, which is given a relation file, you basically build a B+ tree on that file. Okay, so this basically allows you to build an index from scratch. Now one way to do this is to go one record at a time and then use the insert algorithm and then say I'm going to insert one record into an empty tree. What does that mean? You have a single node, root, and then one pointer to a record, that's it. I'm going to insert a second record, second entry added to the root, third record, and so on. That is hugely wasteful because you will have too many index keys and you will have too much I/O. Bulk loading is a process that allows you to reduce the I/O cost because you know what are the set of records that are present a priori. Whereas with an insert procedure, you don't know what the insert key is going to be in the future. Okay, so the way this is done is by sorting the data entries by the index key. So we will talk about the sorting process next class, external merge sort. How do you sort a file that is larger than memory? What if your file is 1 petabyte in size? How do you sort it? So first thing you do is you sort the entire data file based on the index key. And if you have alt record, then that means it's already sorted. So you don't have to worry about the records not being in order. And the process goes as follows. You create an empty root page. You copy the leftmost index key of the leftmost leaf page to the root, and then you assign the child. Okay, so now you create an empty root page. Your data pages are all sorted by the index key. And then you take the leftmost index key of the leftmost leaf page. And then you go left to right in sorted order of the sorted file. And you insert only the leftmost index key from each leaf page into the index. Notice that this means you're bypassing or skipping a lot of records on the page whose index key values could be less than the leftmost key of the next page, but greater than the leftmost key of the previous page. Okay, so this way you're bypassing a lot of potential insert operations because you're operating at the page level. And if you could pack a couple of dozen records into a page, 23 of those index keys are going to be ignored because you're now moving to the next page. When the non-leaf fills up, you use the split procedure and you recurse upwards. Okay, so let's look at an animation for how this works. You have a file with data entries of this form. Let's say each page can contain only 2 entries. First you do an external merge sort. We'll discuss how external merge sort works later, but assume the file is now sorted. All the pages are in increasing order of the keys. All the keys in the page are in increasing order. And then you have this doubly linked list between these pages. Okay, so this is called a sorted file. Start with an empty root, and here the capacity is just 2, so you only can accommodate 2 entries. This is for simplicity of illustration. So the first thing you do is that the leftmost pointer goes to the leftmost page. And the first entry in the root is going to be 5, which is the leftmost key of the next page. Okay, does that make sense? Because the file is sorted, you know, for now let's assume there are no repetitions in the leaf keys. You know anything less than here is going to be strictly less than 5. And therefore, this index key being 5 makes the partial index valid. Now, what do you put here? 14. Why do you skip 7?
Because it's between 5 and...
Exactly. You only need to look at the leftmost key of each page because anything here is by default in between these 2 index key values. And that is because this page, the entire file is sorted in increasing order of the index. Okay, so now next entry you want to add to the root is 17, but there's no space on the root, in the root, so you basically have to split and recall the procedure for insert. When your non-leaf page is reaching full capacity, you have to split it. You push up the middle key and you create a new parent. And so in this case, 14 moves to the new parent. And that becomes a new root. The height of the temporary tree has gone up by 1. Okay? And now this pointer that you had over here is going to be reassigned to this node. Okay? And that means because you pushed up 14, and our convention is that you need to be on the right if you're equal, this pointer has to move over here. Because that means if your search key is 14, you come here, you go right, and then you go left. Okay, so now you keep doing this, and then the next entry you want to add is 20, that goes into that page over there, and then you go add 22, again your node will split, and so you put an entry in there, and so on. Okay? So this is your bulk loading process. In your bulk loading process, you are bypassing a lot of index keys on the leaf level, therefore it is far more efficient than doing a sequence of inserts from the page itself, from the file itself. Yes?
It's possible that you actually like merge the leaf nodes first. Like, is it possible that we actually like merge the leaf nodes first so that we can like, reduce the overall height?
So the leaf nodes are fully packed. There's no free space on the leaf nodes. In this case, the capacity of each leaf node is 2.
Oh.
Because the file is a sorted file, there is no free space on the leaf nodes.
Oh.
Okay, so the free space is only in the non-leaf nodes.
Oh.
Okay, this is another reason why the efficiency of bulk loading is so much higher than doing a sequence of inserts.
We always make sure that the leaf level is always full.
That's only for bulk loading.
Oh.
Okay, so for the bulk loading, the leaf level is always going to be full. That's a good observation. Anything else? Any other questions? Yes?
Are we not giving some excess space in case we want to add more stuff in the future?
That will happen automatically based on the insert algorithm. If you want to add a record here, because there's no space, this will obviously split in the future. And then there will be space. Okay? Anything else? Notice that the occupancy constraint for the B plus tree only says you need to be at least half. It doesn't say you should not be full. Okay, so that's it.